Today we're going to talk about conservation of energy, and we've kind of already looked at it with the lab that you guys did the other day, but we're going to go into more detail with our notes today, go through some examples as well. But you're going to be needing to identify different forms of energy that are present in a scenario, whatever scenario I happen to give you, and then you're going to figure out and learn how to apply the law of conservation of energy in order to write out an energy transfer equation that you can then use to solve for unknown variables. So we're going to look at those things, and obviously more than just that, but in our notes today. So again, please have out some paper so that you can jot this stuff down. You're going to need to be able to do these things in your playlist, and on your roller coaster, so it's kind of important. All right, so how do we know when energy is conserved? What did we say we have to look for to tell if something is conserved?
The same at the beginning and the end.
There you go. Same, it stays the same amount. So same at the beginning as it is at the end. So if I'm specifically talking about energy, that would mean this, that the initial energy would be equal to the final energy, or I could write it in terms of variables. E initial, or E naught, equals E, which is going to be your final value for energy. Again, for whatever the scenario happens to be. This statement, as I've written it, refers to all energy, which would include things like heat and sound and motion and position and any number of other things. Okay. However, I can't measure all of those things. Okay. So if I'm doing a lab, I can't figure out exactly how much heat was generated between the wheels of my cart and the track. I don't know. I don't have a way to measure that. Okay, and so I really don't want to focus on all energy that's present in a system. Now, this is a true statement when we're talking about conservation of energy, but we're instead going to focus on mechanical energy. And so how do I know if mechanical energy is conserved? Again, same idea. If I have the same total amount of initial mechanical energy as I have final mechanical energy. Okay, and the only type of system that is going to be able to conserve my mechanical energy is that isolated system. Okay, remember, open systems don't conserve energy or matter, and closed systems only conserve matter. And so we really want to look at isolated systems, and it's going to be up to us to set up our system in such a way that it is isolated so that we can use the law of conservation of energy. And that's kind of what we're going to talk about today, is what do we need to include in the system. Now, keep in mind that when we do this, this is all going to be like ideal conditions, and it's not necessarily the most real world. That's why our lab data wasn't perfect, because in actuality, we didn't have an isolated system. We can't get rid of some of those external forces that cause our energy to be dissipated from our system, which we'll kind of touch on a little bit later on in the notes today as well. Okay, but again, we're going to focus on mechanical energy. And in our lab, mechanical energy was not conserved because none of those collisions used an isolated system. We could hear sound produced from those collisions. There was friction between those wheels and the track, all of those things. Okay, in the collision where the two carts started and ended separate, we did have conservation of kinetic energy of our system, or at least pretty much. Okay, and we were looking at it through this idealized lens and pretending we can get those perfect results. But we did see conservation of kinetic energy. Okay, and so we said that in the bounce apart collision where the two carts started and ended separate, we had kinetic energy conserved, meaning we had the same amount before and after the collision. And we call a collision where kinetic energy is conserved a perfectly elastic collision. That was something I suggested you write down yesterday in your notes whenever we were going over the lab data. Okay, but those perfectly elastic collisions are going to occur when you have conservation of kinetic energy and conservation of linear momentum. Okay, we've also tested linear momentum in our lab. Okay, the lab we did previous to this is the one where we tested that, and we saw that linear momentum was conserved in all collisions so long as we included the colliding objects. Okay, and so in all of our two-cart systems, we had conservation of linear momentum. But only one of those collisions is perfectly elastic because only one of those collisions also conserved kinetic energy, and that was our bounce-off collision. All of the other collisions only conserved linear momentum, and we call those types of collisions inelastic. Okay, so we have perfectly elastic if we have a bounce apart collision or bounce off, and we have inelastic collisions anytime we have anything else. All right, so as we start thinking about these different types of collisions and interactions, or even just looking at the motion of an object at two different points in time, okay, we're going to start representing the different energy forms that are present with something called an energy bar chart. Okay, and so I've kind of sketched the frame for one up on my screen. I haven't added bars to it yet, but it is a way for us to visualize and to start to think about the different forms of energy that are present in any given scenario. And so you'll typically define some kind of system here, and then in the bar chart itself, you'll label the forms of energy present. For example, let's say that whatever scenario this is, I didn't even label it. Let's say that I started out with gravitational potential energy initially. Okay, this chart is set up so that you can label the different forms of mechanical energy that are present before and after something like a collision, or maybe at two different points in time, an initial point and a final point in time. And so you see here K for your kinetic energy, U sub G for your gravitational potential energy, and U sub S for your spring potential energy or elastic potential energy. And you can draw a bar to represent the energy present. If you have numbers, even better. Okay, right now I'm just showing you what they look like. Okay, and let's say that whatever this scenario is, the object started out with gravitational potential energy, but it ended up with kinetic. And you'll notice that I have drawn it so that the bars are equal. The initial bars will be equal to the final bars if you have an isolated system. And it is up to you to define that system so that it is isolated so that you can use this equation, so that you can set them equal. Okay, if you don't set up your system properly, you wouldn't be able to use conservation of energy. You need to set it up so that it's isolated, so that energy is conserved, so that you can use this information if you're trying to solve for something with conservation of energy, of course. Okay, so let's look at an actual example because this isn't really super helpful out of context. So here's an example. It says, a ball held above the ground is dropped from rest, falls until it compresses a spring and stops. Okay, now if I drop a ball on a spring, yes, it will compress the spring. Yes, the ball will then be flung back up in the air, but I'm not looking at the after the compressing part. Okay, I'm just looking at it compresses it, it stops. I don't care that what happens after that. And so I have an initial point in time and a final point in time. And my initial point in time, I have this ball that is held up in the air. But in order for me to identify the forms of energy, forms of energy that are present, I first need to define my system. Okay, I need to set up my system so that I have an isolated system so that I don't have any external forces acting on the system. I need all of those forces to be internal to my system. Okay, so that it is isolated, so that energy will be conserved. And so, in order for me to do this, can I set up my system as just the ball? No, because if I do that, then things like gravity are external to the system, and I wouldn't be able to account for gravitational potential energy unless I include the Earth. Same thing with the spring. I wouldn't be able to call it spring potential energy or elastic potential energy unless my system included the spring. And so I need to set it up so that all of those forces are internal. I'm going to call this the ball, spring, earth system. And now I have internalized my forces, and now I have set it up as an isolated system, and we're going to assume ideal conditions without any air resistance or friction or anything like that. Okay, so if I do that, I can start out initially, if it's just being held above the ground, what form or forms of energy would I have? What do I have if I'm holding something above the ground? Potential, gravitational potential specifically. So I'm going to draw a bar. I don't have any numbers. I'm just going to draw a bar. I drew it 3 blocks high. Okay, and I'm going to make sure that I keep the same number or the same total height of my bar on the other side. Okay, if it compresses a spring and then stops, first of all, I know I have a compressed spring, but I also know that because it's on a spring, it's not on the ground. And so I would still technically have some amount of gravitational potential energy. I don't know exactly how much because there aren't any numbers, but the remainder would be stored in the spring as elastic potential energy. And I'd have something that looks like this, where my initial bars equal my final bars, and I can write an equation. And that equation is what's going to help us solve problems when we actually, put some numbers to this. And so I have here that the initial gravitational potential energy of this system equals the final gravitational potential energy of the system plus that spring potential energy that we have at the end as well. All right, so again, that's how you're going to use the bar chart to get that equation, and then we're going to put some numbers to it. So let's go ahead and look at another example that has some numbers to it. This one says a 0.02 kilogram marble starts at rest at the top of a 5 meter high ramp. When the marble reaches the bottom of the ramp, it is then launched horizontally off of a 2 meter high table. What is the speed of the marble when it strikes the ground? So I'm going to strongly recommend that for scenarios like this, you draw a picture so you can see what's actually happening, because there was a lot of stuff in that question. And so here I have my 5 meter high ramp sitting on top of my 2 meter high table. This is obviously not to scale, that's okay. Okay, and I have my marble starting up here at rest, rolling down the ramp, and then it launches off horizontally like a projectile, landing somewhere over here with some amount of final velocity. And that's what we're trying to find, is how fast it's going just before it hits the ground. Okay, and so again, I would encourage you to draw a picture of something like this. But again, we're looking at 2 points in time, specifically the 2 points that they told us about. We know that the marble was started at rest, and we know that it started at the top of this ramp that's sitting on top of this table. And so I know that the initial state of this marble, that it has gravitational potential energy. Okay, so long as I set up my system so that it's isolated, which means what has to be in my system? Earth. Not just Earth, though. What else do I need in my system? The marble, yeah. Okay, so I'm going to call this the marble Earth system. I need to set it up so that it's isolated, so that that force of gravity is not an external force on the marble, but rather is an internal force in the marble Earth system that gives me gravitational potential energy. So I'm going to draw a bar for gravitational potential energy. And again, I don't have any numbers yet for the amount. I'm just going to draw a bar. Okay, and I do need to set it up so that I have the same amount of energy at the end, because I set up an isolated system. That should mean that my energy has been conserved. And at the end, just before this marble hits the ground, the only form of energy present, because it's basically on the floor, is kinetic. Okay, it has lost all of its height, is basically on the ground. This is the instant before it hits. Okay, and so all of that is now kinetic. So those are the 2 points in time I'm going to look at, and I can write an equation. My initial gravitational potential energy will equal my final kinetic energy. And I can use that equation to answer the question, because the question wasn't draw a bar chart. The question was, how fast is it going? Okay, given this information. So let's use this equation to figure out how fast it's going. Okay, now this equation is not going to help me with how fast it's going, but I do have equations for both gravitational potential energy and for kinetic energy that have other variables in them. So we're going to substitute those in. Gravitational potential energy is mg delta y. Sometimes you'll see it written as mgh. H is height, delta y is vertical displacement. They can be used interchangeably. Okay, and so that's my equation for my gravitational potential energy. My kinetic energy is 1/2 mv squared. I'm trying to solve for that v, that's why I made it yellow, which means I need to get that by itself. So let's go ahead and start by rearranging some things so we can isolate that variable. I'm going to start by multiplying both sides by 2, because that'll cancel out this half, and it leaves me with this. 2 times mg delta y equals m times v squared. Now again, if we're trying to isolate v, we need to divide both sides by m. If I divide both sides by m, my masses cancel in this particular equation that I've written. Okay, and so apparently mass has no bearing on this whatsoever. It could be a really big marble, a really small marble, wouldn't matter, theoretically, if everything else was the same and there's no air resistance. Okay, so I have 2g delta y equals v squared. Again, I want v, not v squared. Square root both sides. And I get this. Velocity of my marble just before impact is equal to the square root of 2g delta y. Now we can plug in our numbers. I know g, gravitational field strength on Earth, is 10. I know the height it's the 5 plus the 2, since the ramp is on the table, so it's a total height of 7. So 2 times 10 times 7, all of that under the radical, all of that is equal to 140, and so the square root of 140 would be my velocity, which gives me a value of 11.83 meters per second. And again, we're assuming a lot of things here because we set up our system as isolated, and we're assuming that we don't have any of these other external forces like friction or air resistance. Just out of curiosity, if we did have external forces like friction or air resistance, would my velocity still be 11.83 meters per second in this same type of scenario? No. What would you expect it to be? Slower, yeah, less. Okay, so you could have a question like that, okay, or maybe the question gives you the same information, but it tells you, hey, if the marble's going 7 meters per second when it hits the ground, you would look at that and be like, but it's supposed to be almost 12, so clearly there's something else going on. Okay, so again, another type of question to think about that you might end up seeing, but you could have dissipated energy in that case if you had a scenario set up like that. Okay, but again, we're trying to set up our system so that it's isolated so that we don't have that, so that we can use our conservation of energy to solve for things like this. All right, guys, for the rest of the class period, you can work on playlist 3, which includes assignments like 512 and 513. That worksheet practice is on paper. You should already have a copy of it, but don't forget you do have to turn it in digitally as well, turn in pictures of it. But you can work on that or the quiz that's in there. You also have your lab, of course, that you can work on. It is due on the 26th, but if you want to turn it in for feedback, you can do that today. And then your preliminary data for your roller coaster. Tomorrow is the deadline for the roller coaster preliminary data. If you haven't looked at the roller coaster sheet yet, you might want to pull it out and see exactly what that entails. Make sure you know what you need to do to get that done and turned in. It's turned in on paper, which means it's turned in before you leave the room tomorrow. Okay. However, tomorrow is a roller coaster Q&A day, so you'll have the entire period to work on the roller coaster, just like you have the entire period right now that you could use for the roller coaster or for any of these things. Okay. If you have questions as you're working, guys, please let me know.